This word is important because later on, not in this course, but later on you will come across discrete time Fourier transforms, discrete time Fourier series and discrete time Fourier transforms. So whatever we are discussing in this course, they are all for continuous signals. Fourier analysis for continuous time signals. Yeah. So just before starting today's class, let's quickly recap yesterday's like the previous class, not the entire previous class, but this last concept. So what we did, what Fourier series is allowing us to do is, if there is a periodic signal x of t with period capital T, with period capital T, so that its fundamental frequency is equal to 2 pi by t, then we are able to express this x of t as a weighted linear combination of exponential signals. So it's a weighted linear combination of a1 e power j omega naught t, a2 e power j omega naught, e power j2 omega naught t. So these frequencies, omega naught, 2 omega naught, 3 omega naught, or so these are all called harmonics of the fundamental frequency. So this is the fundamental frequency. This is the fundamental frequency of the signal x of t, and this is the second harmonic, this is the third harmonic, and so on. Of course, we should also consider plus or minus, plus or minus, plus or minus. Like if omega naught t is the fundamental frequency, so is minus omega naught t, and so this is 2 omega naught t and minus 2 omega naught t, and so on. So what I'm trying to say is, signal, we are expressing that as a linear combination of harmonically related exponentials, and these coefficients a0, a1 plus a1, a minus 1, a2, a minus 2, a3, a minus 3, they are all called spectral coefficients. They together they are called a spectrum of the signal x of t. Means it tells us in the signal x of t, how much of x of t is composed of a frequency at 2 omega naught t, right? So and so on. Yeah, so this we need not, I'm just erasing this because in the last class we didn't have it. You don't need to strictly have it, but just for the explanation's sake. Yeah. So now let's start with continuous transforms. So one of the main thing that you should know is Fourier series is applicable only for periodic signals, right? We assumed a periodic signal x of t, and then we did the Fourier analysis. So now the question we ask in this chapter is, can we extend or can we do, or can we also represent an aperiodic signal? Periodic means it's not a periodic signal, right? An aperiodic signal in the similar manner as a weighted linear combination of, and another thing to remember for you is that this Fourier series is nothing but orthonormal expansion, where the orthonormal functions are exponentials, complex exponentials. So what we did was x of t x of t we have represented as a weighted linear combination of complex exponentials. So can we also do such a thing as a weighted linear combination of orthonormal functions? More especially we are interested in complex exponentials. Yes, so it turned out that we can do such an analysis even for continuous time aperiodic signals which are not periodic, and the most intelligent way of dealing this was done by Fourier way back in 1800s. So by Fourier achieved this by considering, see, the trick is simply the same. An aperiodic signal he considered as a periodic signal with infinite period. So we'll study this concept in detail in the next few minutes. So he did this by Fourier achieved this by considering an aperiodic signal as a periodic signal with infinite period, with its fundamental period is equal to infinite. So this is the most important concept of Fourier transforms. And okay, so that's all for the history, and then let's get started with it. To motivate how we can define Fourier transforms, we will quickly revisit one of the examples that we did in the previous class, which is a periodic square wave. And then, so this example is only to motivate us, or only to show how Fourier transforms can be defined for aperiodic signals. And then we will formally define and then go ahead. Okay, so let's revisit this example. Periodic square wave example. So if you have looked at the previous class notes, you can immediately recognize that this square wave is something like this. Yes. So this is minus T1 by 2, and this is T1 by 2, and say this is T by 2, this is T by 2, this T, this T, and then here again we have this signal. And so on. So this is a periodic square wave x of t. So how did we express this signal? We expressed this signal over one period. So x of t over one period. Remember this, over only one period can be expressed as it is equal to 1, 0, modulus of t is less than t1, and t1 less than or equal to modulus of t less than or equal to t by 2, right? So this was our signal over one period. So here the period can be from 0 to t or from minus t by 2 to plus t by 2. So we use this integral from minus t by 2 to plus t by 2 to find out ak equal to. So if we did this integral minus t by 2 to plus t by 2 x of t e power minus j k omega naught t dt. Then we did this in the last class, so I'm not repeating that. Is equal to 2 sine. Let me look at my notes. 2 sine k omega naught t1 divided by k omega naught t. Yeah, for k not equal to 0. Yep. So we till this point we did in the last class when we dealt with Fourier series. Now we want to move ahead of Fourier series. We want to introduce Fourier transforms. So let's have a relook at this example. So this can be interpreted as, see what this gives you. What this gives you is what is the value of a1, what is the value of a2, and so on, right? So this can be interpreted as this t, I'm taking it to the left hand side, so this will be tak. This I can write as sine omega t1 divided by omega. So this divided by omega sampled at omega equal to k omega. So the same expression we are interpreting that as this ak, the value of the Fourier series quotient multiplied by the period. So tak. So tak can be considered as samples can be obtained by sampling the function 2 sine omega t1 by omega. So in this equation, if I put omega is equal to k omega naught, I get the above function, right? So this above function can be obtained by putting omega is equal to k omega naught here. That meaning previously with this what we have was, so this is index of k 0, k equal to 1, k equal to 2, k equal to -1, k equal to -2. So you have some value of k, a1. So this is a1, and maybe this is a2, and maybe this is a3, then this is a4, and so on, right? Now what we are saying is that the same thing can be obtained. This can be considered as, okay, so here let's say this is a naught, this is a -1, this a -2, and so on. So this can be, what we are saying is that this can be considered as this function. This is 2 sine omega t1 by omega, and is being sampled at k equal to 1, k equal to 2. This is also again k, and this -1, -2, and so on. So this envelope is, what is this function? 2 sine omega t1 divided by omega, right? And the most important thing to be considered here is as t increases, this sampling. Okay, so uh, so in the second case here, let me, okay, so let me go to the next page. As t increases, omega naught equal to 2 by t, sorry, 2 pi by t decreases. So the function sine omega t1 by omega is sampled at much closer intervals as t increases, because omega naught decreases, right? So what, so we'll finish this. So what I'm trying to say is, this is omega and this is tak, and this is the function 2 sine omega t1 by omega. So this is being sampled at, previously this is omega naught, and this point is to omega naught. This minus omega naught, and this point is minus 2 omega naught, and so on. So this is for capital T equal to 4t1. So I have taken this function and I simply put capital T equal to 4t1, or capital T1 is equal to t by 4, and this, so and when t equal to 4t1, and we are sampling it k into omega naught t, which is equal to k into 2 pi by t, right? So if I increase k, if I increase t into 4t1, then what happens when sorry, to 8t1, what happens is, when t becomes 8t1, these samples will become closer, because omega naught, so this is one omega naught, this is another omega naught. This omega naught has become reduced, so this omega naught becomes reduced, and what I will get is much more closely spaced samples. So something like this. Say this is a function again. So this is still the same function, 2 sine omega t1 by omega, but now I have this omega naught to omega naught, 3 omega naught, and this will be 4 omega naught. So the samples will be something like this. So this minus omega naught, minus 2 omega naught, minus 3 omega naught. This is minus 4 omega naught. So as t increases, so you see, you need not remember this exact diagram, or you need not mug up anything in this concept. The only thing I'm trying to say is, as the period t increases, these samples becomes closer and closer, and when t becomes infinity, these samples are placed next to each other. The spacing between the samples becomes infinitesimally small. So as t goes to infinity, the spacing between the samples becomes infinitesimally small. Right? So that's and your summation becomes an integral. So previously your Fourier series has consisting of samples something like this. So these are the samples of your Fourier series. Now as t becomes infinity, they okay, so I have drawn a different function. So this function is okay. So let's go ahead and define. So let's go and define a Fourier transform. So what I tried to motivate in the previous example, if you are confused about what we did in the last two pages, what we tried to say is, we have taken a periodic signal and we made this period goes to infinity. So we found the Fourier series quotients of this signal for a fixed period t, and then we just did an experiment what happens when t goes to infinity. So when t goes to infinity, these Fourier series quotients come closer and closer. So they become very closely spaced, and when exactly t becomes infinity, they become so closely spaced that it becomes a continuous function. The Fourier series is no longer a Fourier series, but it becomes a Fourier integral. And hence, yeah, I can write this. The Fourier series becomes let me write this. The summation, that means the sigma term, in the Fourier series becomes an integral yeah. Right. So yeah, so note down this sentence. The summation becomes an integral, and then now consider formally how do we define Fourier transform. Consider a signal x of t of finite duration, because that means a periodic. We want to consider a periodic signals, right? So that meaning it has got a finite duration. So any periodic signal has infinite duration. Is that right? Yes, right? Because x of t plus capital T, where capital T is the period, should be equivalent to x of t. So when x of t is periodic with period t, it should also be periodic with period 2t. It should be periodic with period 3t, and so on. So any periodic signal extends infinitely in time from minus infinity to plus infinity, whereas a periodic signal will be having finite duration in time. So we are trying to say x of t is equal to 0 for mod t greater than t1, right? So that meaning we just have a signal something like this. So we take an example where, say, this is the signal. Say this is minus t1, this is plus t1, and this is x of t. So from this signal, let's construct x tilde of t. Okay, let's construct a periodic signal. Let me write that. Construct a periodic signal x tilde of t for which x of t is one period. So what I mean to say is that you have a periodic signal x of t. So x of t is 0 everywhere else. It is non-zero only from minus t1 to plus t1. So from this a periodic signal, construct a periodic signal x of t. Say this is 0, right? And then, so this is t1, is minus t1, and we are constructing x tilde of t. So minus t, so plus t, this is 2t. So you just, what we are trying to do is, we are constructing a periodic signal for which in this period, so in this is minus t by 2, this is t by 2. So this is one period, right? So in this one period, x tilde of t is equivalent to x of t. That's what I'm trying to say here. So construct a periodic signal x tilde of t, right? And in x tilde of t, x of t is equivalent to one period, right? Now this is your periodic signal, and now as the period goes to infinity, x tilde of t becomes x of t, right? Because in this, now I move these other signals, this t, I make it, if I make t very large, these two signals will go far away, and if I make t almost infinity, it becomes x of t. Now x tilde of t is a periodic signal, right? So consider its Fourier transform, Fourier series. We know that any periodic signal, of course, if it satisfies the Dirichlet's conditions, and here this signal satisfies the Dirichlet's conditions. If it satisfies Dirichlet's condition and if it's a periodic signal, we can find its Fourier series. So let's consider x tilde of t. The Fourier series of that is given by ak e power j k omega naught right? And then where AK can be considered as, okay, this will write in the, where AK can be considered as 1 by t, and it's over one period. We have to do the integral minus t by 2 to plus t by 2 x tilde of t power minus j k omega naught t dt. And you should also know that this is equal to 2 pi by t, right? So this, now I can write this as, see, the important step is minus t by 2 to plus t by 2 x of t e power minus j k omega naught t dt. Why is this possible? Because x tilde of t is equivalent to x of t over minus t by 2 to plus t by 2. This is because x tilde of t is equivalent to x of t over a single period from minus t by 2 to plus t by 2, right? So this you can also see from the diagram. X tilde of t is exactly equivalent to x of t over period minus t by 2 to plus t by 2. Now a further modification is, now look at x of t. So x of t is defined only from minus t1 to plus t1, and it is 0 everywhere. So here it is minus t by 2, here it is t by 2, right? So x of t is non-zero only from minus t1 to plus t1. See that we have also written here. X of t is 0 for the time intervals greater than t1, or it is non-zero only in this interval. So that's why I can write this integral is, I can write this as minus infinity to plus infinity x of t e power j k omega naught t dt. How can we write this? This is because x of t is 0 except in the interval minus t by 2 to plus t by 2. So that's why I can write this, right? So this again I am trying to express this as 1 over t x of j omega at omega equal to k omega. So this k omega naught, I can further write that as omega naught is equal to 2 pi by t. Okay, so right now we don't need this, where x of j omega is equal to 1 by t integral minus infinity to plus infinity e power j omega e power j omega t, yes, yeah, e power j omega t dt, right? So these steps, now we are here. So this, I can write this as 1 over t, and this entire thing I can write it as x of j omega. And so you just right. So this can be written as something like this, and so so just for convenience, let me write that what we did was x of j omega is minus infinity to plus infinity x of t e power j omega t dt, and with that we can write x tilde of t. See, all this we are doing just to express x of t, sorry, x tilde of t as a Fourier series expansion, e power j k omega naught t, k equal to minus infinity to plus infinity. So this, now what we got was 1 over t x of j k omega naught e power j k omega naught t, because ak is 1 over t x of j omega sampled at omega equal to k omega naught t, that is nothing but 1 over t x of j k omega naught. Where x of j omega is given by 1, where this is the one, equation 1. Yeah, so now let's do one last trick here, and then we are done with the Fourier transforms. Like at least we complete the definition of Fourier transforms here. So this 1 by t, I can put t is equal to 2 pi by omega naught. So if I put that, it becomes x tilde of t is 1 by 2 pi k equal to minus infinity to plus infinity x of j k omega naught e power j k omega naught t into omega naught. So what we did was, we are given a signal x of t which is aperiodic and which is of finite duration. Like x of t is finite duration and it is non-zero only from minus t1 to plus t1. From that x of t, we constructed a signal x tilde of t. So let's go back here. So what we did was, we are given an x of t, and from that we computed x tilde of t. We constructed x tilde of t, which is a periodic signal, and then we were trying to compute the Fourier series coefficients of x tilde of t. So x tilde of t we want to express as summation ak e power j k omega naught t, and in that process we are trying to find ak. So ak, from the formula it is given by this, but x tilde of t equal to x of t over this period. So we did that, and then as x of t is 0 from minus infinity is 0 except during the duration of minus t by 2 to plus t by 2, we can replace this integral from minus infinity to plus infinity, and then we did some manipulations to get this thing. But now what we need to do is, we want to find the expression for x of t, not for x tilde of t. And we know that x of t, x tilde of t becomes x of t when t becomes infinity. Right? We know that x tilde of t becomes x of t when t goes to infinity. So when t goes to infinity, you can check mathematically that the equation 1 over 2 pi x is equal to minus infinity to plus infinity x of j k omega naught e power j k omega naught t omega naught becomes simply an integral, because as t goes to infinity, omega naught goes to very, very small, almost zero, right? So what it becomes is x of j omega e power j omega t d omega. And these limits becomes from minus infinity to plus infinity. That implies x of t can be expressed as 1 over 2 pi minus infinity to plus infinity x of j omega e power j omega t d omega, where x of j omega can be computed as minus infinity to plus infinity x of t e power minus j omega t dt. This is the Fourier transform of an aperiodic signal x of t. So this is the Fourier transform equation. This is the Fourier transform this is also called Fourier integral. Fourier transform or Fourier integral equations for an aperiodic signal x of t. So given an aperiodic signal x of t, that can be expressed as 1 by 2 pi my integral minus infinity to plus infinity x of j omega e power j omega t d omega, whereas this x of j omega can be computed as the integral given below. So this is equivalent to, so just compare this with your Fourier series. In Fourier series, here you have a summation sigma k equal to minus infinity to plus infinity, and then here you have ak, and here you have e power j k omega naught. So all these summations becomes integrals, and your sampling will become much closer and closer. So in these two equations, this is called the Fourier transform. This is called a synthesis equation, and this is called the analysis equation. So simply to sum up, whatever we did in the last 1 hour is just to explain the concept of Fourier transform, how Fourier transform can be defined, for aperiodic signals, and how we derive that from the Fourier series. See, we can also do one thing, that we can only state these two equations and say that this is the Fourier transform of an aperiodic signal. But historically and even mathematically, the Fourier transforms have been derived from Fourier series. So you should be knowing how they are derived from Fourier series. They are derived by considering an aperiodic signal as a periodic signal with period going to infinity. That is the main trick Fourier has used. Right? So from now on, we'll just take these two equations and then do a whole lot of things like properties, and we'll compute Fourier transform for different signals and so on and so forth. So just to continue with this, so let me. So I'll. So in these equations, x of t, no. So now I'm talking about these two equations. We will talk about only these two equations further. So in these two equations, we can write x of j omega is called the Fourier transform of x of t. And x of t is called the inverse Fourier transform of x of j omega. So this x of j omega is the Fourier transform of x of t, and x of t is the inverse Fourier transform of x of j omega. So this inverse notation, you don't have it in Fourier series, right? So this is one of the new concept. So if you are given a time domain signal, you can find its Fourier transform by using this second equation. And if you are given a frequency domain signal, because omega is the frequency, right? So this signal, this is considered to be in the frequency domain. Then you can find a corresponding time domain version of this signal by using inverse Fourier transform, right? And also okay, then we'll do some examples, and then what else we need to discuss. Yeah, so x of j omega, there is one more point, then we'll go to some examples. X of j omega okay is also called the spectrum of x of t, because it gives information required to express x of t as a summation of integrals. So let me state that it gives us information required to express x of t as a linear combination see here the linear combination should be taken as integral. So linear combination is not strictly in the form of summation, but it's in the form of integral. As a linear combination of sinusoidal signals. Why do I call sinusoidal signals? We used only complex exponentials, right? But why am I calling that calling them a sinusoidal signal? Because e power j omega is nothing. J omega t is nothing but cos omega t plus j sin omega t at different frequencies. So it gives us information required to express x of t as a linear combination of sinusoidal signals at different frequencies. As a linear combination, here the linear combination is nothing but the integral of sinusoidal signals, where the sinusoidal signals are expressed in terms of complex exponentials and they are at different frequencies. These complex exponentials are at different frequencies. So but are they distinctly different frequencies? Like are they e power j k omega t where k is equal to 1, 2, 3, 4, etc.? No. These different frequencies are continuum of frequencies. Continuum meaning they are not distinct, there is no finite spacing between these frequencies, but the spacing between these frequencies is infinitesimally small, like it's delta, where delta goes to 0, right? So that's why this x of j omega is called spectrum of x of t. Yeah, so now let's quickly write down one of the next important topic is okay. So yeah, so we all that we did till now is only defining the Fourier transforms. It's not only defining but trying to derive them from Fourier series. As I said, we can define them in 10 minutes, but we have to be understanding how they came up into existence from Fourier series, how people thought about having Fourier transforms. And as I said, one of the main motivation for having Fourier transforms is that we want to represent a periodic signals also as a linear combination of complex exponentials, or we want to represent periodic signals as a linear combination of orthonormal signals. That's why we derived this. Now, if you recall Fourier series, there are three Dirichlet's conditions. Like given any periodic signal, can you find Fourier series? Right? If you are given x of t and x of t is periodic, can you give a guarantee that Fourier series exists for that signal? No, you can give guarantee only if x of t satisfies Dirichlet's conditions. So we stated three conditions: that it should be square integrable, it should have only finite maxima and minima in a given period, and it should have only finite number of discontinuities in a given period, and that too these discontinuities should be finite. So there were three Dirichlet's conditions in case of in case of Fourier series. Similarly, here for the Fourier transforms, we will have three Dirichlet's conditions. So given an aperiodic signal x of t, we will say that Fourier transform exists for this x of t only if x of t satisfies all the three Dirichlet's conditions, right? So let's write down this. For a signal x of t to have a Fourier transform, it should satisfy the following conditions. Known as Dirichlet's conditions, because these are given by the scientist P.L. Dirichlet. So one is x of t should be, condition one is x of t should be absolutely integrable. So here it is not square integrable, it is absolutely integrable. So that meaning, what does this mean? X of t mod, it's the modulus of x of t dt should be less than infinity. So this is condition one. Condition two is x of t should have only a finite number of maxima and minima over any finite interval like you consider a finite interval, anything from a finite interval of duration some tau. So in that finite interval, it should only have a finite number of maxima and minima. It should not have infinite number of maxima and minima. That is condition number two. And condition number three is x of t should have only a finite number of discontinuities within any finite interval and each of these discontinuities must be finite. So if a signal x of t satisfies all the three conditions, then it is guaranteed to have a Fourier transform, right? And in fact, these are the very famous set of conditions, Dirichlet's conditions, and Yeah, as you know, for undergraduates, for BTech students, this forms one of the most important topic in Fourier transforms or Fourier series. So these Dirichlet's conditions, and then in fact there is one more equivalent condition. Another equivalent condition. Another equivalent condition. Equivalent condition for what? For for the Fourier transform to exist. Another equivalent condition is that x of t should be square integrable. That is, if simply x of t is square integrable, dt is less than infinity, that which implies that x of t has got finite. And okay, so what is this integral? Integral minus infinity to plus infinity modulus of x of t whole square dt. So this is nothing but energy of the signal x of t, right? So when this square integrable, when a signal x of t is square integrable, that means it has finite energy. So x of t has got x of t has got finite energy. Then also x of t will have a Fourier transform, right? So this condition is equivalent to the Dirichlet's conditions, but Dirichlet's conditions gives a more detailed view of what the signal should be in order for it to have a Fourier transform. Whereas this condition doesn't, like, it encompasses all the three conditions, but there are there are micro differences between these two. Micro differences in the sense, if a signal x of t satisfies Dirichlet's conditions, then what is the equivalence between x of t and its Fourier transform x of j omega? And if the signal satisfies the finite energy condition, what is the equivalence between x of t and x of j omega? So these two are, there is some finite differences. Will like Yeah, so we don't need to go much depth into that aspect. So with that, let's consider some of the examples. So let's consider x of t is equal to e power minus at u of t for a greater than 0. Right? So we are given a finite duration signal e power minus at u of t. See, because u of t is greater than 0 only for t greater than 0, this signal is non-zero only for t greater than 0, right? Note that u of t is equal to 1 for t greater than or equal to 0 and is 0 for t less than 0. So that's why this x of t yep. So this is e power minus at u of t, right? So this x of t. This is t. Now, what is its Fourier transform? X of j omega is integral minus infinity to plus infinity e power minus at u of t e power j omega t dt. So this I can write this as 0 to infinity because u of t is 0 from minus infinity to 0, right? So u of t is non-zero only from 0 to infinity. So this will be e power minus at into e power j omega t dt. So this simply e power j a plus omega t. Oh, sorry. Yeah. J into a plus omega t. No. See here, it is a plus j omega. A plus j omega into t. So t is here. Right. A plus j omega t dt. And if we do this integral, what we will get? 1 by a plus j omega. So you can check this integral. It becomes okay. Then another mistake. So today there are multiple mistakes. Because it is from 0 to infinity, it should be 0 to infinity, and it is wait a second. The equation, it should be e power minus j omega t. Yeah, so I'm very sorry for the mistake. So x of j omega is minus integral minus infinity to plus infinity x of t into e power minus j omega t dt. So this minus sign, it should be there because we are correlating x of t with all the complex exponentials, right? Okay, it's minus j omega t. So it is e power minus at e power minus j omega t dt. So yeah, so this becomes integral 0 to infinity e power minus a plus j omega t, so on. Okay, so one thing we should note that x of j omega is equal to 1 plus a plus j omega is complex valued function, is a complex valued. So to plot this, we need to plot, say for example in your exams, if you are asked to plot Fourier transform of a signal x of t. So you can find Fourier transform by simply applying the formula x of j omega. But when x of j omega comes out to be a complex valued function, then you should have two plots in your answer. To plot this, we need to plot both the magnitude and phase of x of j omega. That meaning you have to plot the magnitude. So here, what is the magnitude? A square plus omega square. That is the magnitude, right? What is the angle of x of j omega? x of j omega is tan inverse w by a. Okay, so this is 1 by a plus j omega, so it should be minus of tan inverse because it is in the denominator. The complex number is in the denominator, so your phase will be negative of tan inverse w by a, right? So the plot should be something like this. I'm not plotting that you can do it. So it should be with omega, and this should be y-axis should be magnitude of j omega, and it should be omega, and it should be angle of x of j omega. So complete the plots as a homework, right? So we'll do a few more examples because these examples will tell you what are the Fourier transforms for some of the basic signals. See here we considered e power minus at, which is a complex exponential signal, e power minus at. Of course, we truncated that only, we limited that only from 0 to infinity. So another example, x of t is e power minus a modulus of t. And here also we are giving the condition that a is greater than 0. So if a is greater than 0, we know that whether it is a decaying exponential or growing exponential, right? So that a greater than 0 or less than 0 is important just to know that. So how does this signal looks? This e power minus, the signal will be something like this. This is e power minus at and this is at, because, right? So this is with respect to t. Right. So how do we compute its Fourier transform? Fourier transform of x of t is equal to e power minus t. So x of j omega is equal to minus infinity to plus infinity, x of t e power minus j omega t dt. So this is equal to minus infinity to 0 e power at e power minus j omega t dt. I'm splitting this interval into minus infinity to 0 and then 0 to infinity. Then in minus infinity to 0, e power minus a into modulus of t becomes e power minus a into minus t. So that becomes at. So in the interval from 0 to infinity, it becomes mod of t becomes t. So it will be e power minus at. Right. So this, can you complete this out? So this is another of your homework. So then we'll take another example. So this example is rather more interesting because it's the find the Fourier transform of unit impulse delta of t. So what is delta of t? If you remember this from some of our previous classes, this is t and delta of t. So delta of t is equal to 1 for t equal to 0 and is 0 elsewhere, right? So its Fourier transform is very easy. X of j omega is minus infinity to plus infinity delta of t. So it becomes 1 only at one value at t equal to 0, and at t equal to 0 e power minus j omega t is equal to 1, so it will be 1, right? So that meaning the Fourier transform the Fourier transform, its x-axis is omega. This is equal to 1 for all values of omega. So this will be x of j omega. So this is x of t. Yeah. So we are given x of t is equal to delta of t. This is equal to delta of t. So that meaning Fourier transform of an impulse function, unit impulse function, is constant. So what does it mean from the frequency spectrum point of view? So what we said was x of j omega tells us the spectrum, like what are the frequencies present in x of t. So from here it is understood that the spectrum of delta of t, so the spectrum of a unit impulse, the spectrum of delta of t contains equal contribution from all the frequencies from minus infinity to plus infinity, right? That's why that's how we got this Fourier transform of delta of t equal to 1. So what we can write about this is the Fourier transform of delta of t has equal contribution from all the frequencies. Right? And then we'll do this rectangular pulse. So the next example is rectangular pulse. So this rectangular pulse is nothing but it's a pulse from minus t1 to plus t2. So it is minus t1 to t1 so x of t can be expressed mathematically as is 1 for odd t less than t1 and it is 0 elsewhere. So again, how do you find the Fourier transform? Fourier transform is straightforward. X of j omega is equal to minus t1 to, okay. So see here, I need not write the integral limits from from minus infinity to plus infinity, because x of t is non-zero only from minus t1 to plus t1. So this is equivalent to 1 multiplied by e power minus j omega t dt. So this, after doing some manipulation, what you get is x of j omega is equal to 2 sine omega t1 divided by omega. Yep. So here x of j omega is a real valued function. Right? And then you need to draw no, you need to draw only one plot whenever x of j omega is a real valued function, right? So just as a last example, what should we take? Okay, so last example we'll take so last example is example 5, and this is okay. In all the previous examples, what we did was, if we are given x of t, then we tried to find its Fourier transform x of j omega. Now we will do the other way. We'll do the other part of it, in the sense, if we are given x of j omega, right? If we are given x of j omega, we have to find x of t. And if you recall, we called x of j omega as the Fourier transform and x of t as the inverse Fourier transform. Getting x of t from x of j omega is kind of finding inverse Fourier transform. So let's computing. So this example is computing inverse Fourier transform. Let a signal let a signal x of t has Fourier transform x of j omega given by x of j omega is equal to 1 for omega less than capital W, and this is 0 for omega greater than or equal to the No. This should be modulus of. Yeah. Yep. So that meaning our x of j omega yep, this is x of j omega, and then we have to find now find x of t. So x of t is equal to 1 by 2 pi minus infinity to plus infinity x of j omega e power j omega t, right, d omega. But that this is again, this kind of integral we already did 2-3 times till now. So this becomes 1 over 2 pi, and this is from minus w to plus w, and this is equal to 1 and e power j omega t d omega. And after doing some manipulations, what you should be getting is sine wt by pi t. So complete the steps, or we can also say fill in the blanks, right? Yeah. So here also there is a function x of t is something like sine wt divided by pi t. See, and previously here also we got a function which is sine wt1, sorry, it's not w, sine omega t1 by omega. So there is an independent variable omega here, and there is the same independent variable here in the denominator. So sine omega t1 divided by omega, and here it is sine wt. Here the independent variable is t, it's not omega, right? So it's sine wt divided by pi t. So there is an independent variable in the numerator and the same independent variable in the denominator. So for functions of this sort, these sort of functions keep coming regularly in signals and systems, in analog communications, in digital communications, in digital signal processing. So in dealing with fundamental signals, this kind of signal sine pi theta by pi theta kind of signals will keep coming. So we'll give it a name for this special signal. So we define sinc function. So sinc function is given by sine pi theta by pi theta, and this can be, see, if some of you knows the software MATLAB, So it goes it expands, it extends from minus infinity to plus infinity. So this is a symmetric signal around 0 and its peak value equal to 1. So this is sinc theta. This is independent variable theta, and then these are the values of 1, 2, 3, 4, and so on, minus 1, minus 2, minus 4, and so on. So this sinc theta has 0 value at all integer multiples of theta except at theta is equal to 0. So 0 at all integer values of theta except at theta is equal to 0. So why did we define sinc function? We wanted to express the previous signals, some of the previous signals as sinc function, right? Say for example, previously we had some of the signals as 2 sine, it was omega t1 by omega, and we also have 2 sine, so this is w t divided by pi t. So this can be written as two sine omega t1 divided by omega can be written as 2t1 sinc w t1 divided by pi sinc omega t1 divided by pi. And similarly we can write sin wt by pi t. W by pi So you know the definition of sinc theta, and then you have to express this signal in terms of sinc signals. Sorry, this should be sinc. So this should be sinc of wt1 by pi. So this should sorry, omega t1. So this is omega, this is w. Okay. So we'll do just one more example and then we'll stop for today, right? So we'll do one more inverse Fourier transform. So let's do this one more impulse Fourier transform. So this will lead us to an important signals set of signals called Fourier transform of periodic signals. See, Fourier transforms are defined only for periodic signals. But if we allow impulse functions, then we can also define Fourier transforms for periodic signals, as can be seen from this example. So this example motivates us. Say for example, you have x of j omega is equal to 2 pi into delta omega minus omega naught. So what is this? This is an impulse of strength 2 pi or area 2 pi at frequency omega naught equal to omega naught. So its Fourier transform is x of t is minus infinity to plus infinity x of j omega e power j omega t d omega. Sorry, I forgot 1 over 2 pi. So this becomes 1 over 2 pi minus infinity to plus infinity 2 pi delta of omega minus omega naught. This 2 pi gets cancelled. E power j omega naught omega t d omega. So this impulse becomes non-zero only at omega is equal to omega naught. So this becomes simply e power j omega naught. See, this is nothing but a complex exponential. This is a complex exponential, right? At frequency omega naught. And more importantly, this is a periodic signal. So what does that mean? If we have a complex exponential e power j omega naught t, then its inverse Fourier transform, then its Fourier transform will be 2 pi into delta of omega minus omega naught, right? So this is a periodic signal. So this means that this means a very big thing for us. This shows that we can define Fourier transforms for even periodic signals, or let's call it for periodic signals also. So we started our derivation of Fourier transforms considering only on non-periodic signals like aperiodic signals, but now we are finding that even for periodic signals we can have Fourier transforms. Of course, the Fourier transform of periodic signals consists of impulse functions, just like that 2 pi into delta of omega minus omega naught. So, but even then, that means Fourier transforms is more generic. So Fourier transforms can be applied to periodic or aperiodic signals, whereas Fourier series can be applied only to periodic signals, right? So Fourier transform is a more general tool as it is applicable to both periodic and aperiodic signals, right? So what does this mean? Fourier transform of e power j omega naught t is equal to 2 pi into delta of omega minus omega naught. Now, what is the inverse Fourier transform of 2 pi ak delta of omega minus right? So we have found the inverse Fourier transform of 2 pi into delta of omega minus omega naught. So now we are trying to find the inverse Fourier transform of this whole bunch of signals. So we can show that, or as homework, show that inverse Fourier transform is given by ak e power jk omega naught t, k equal to minus infinity to plus infinity. Right. So we'll stop here for today's class, and if you have and if you have any free slot either tomorrow or day after, let me know so that we can have an extra class, because your exams are starting from August 6th, the coming Monday. So if we have any extra slot either tomorrow or day after, we can have an extra class where we can discuss the properties of the Fourier transforms. So